everybody, and welcome to our combined lecture for hypothesis testing and randomization testing. Just like in our previous lecture, this topic is discussed in the textbook, but it's discussed in a more traditional computational way that we're trying to avoid in this course. Because of that, the way that we're going through these topics is going to be off book. So if you have questions, the textbook in this case won't be your primary resource. If you have questions, read through the PowerPoint, which I will upload to Blackboard, watch the lecture video that you're currently watching right now, and then email me with any questions that you have, or send these questions on WebAssign. Let's get started. Hypothesis testing and randomization testing using StatKey. First, a hypothesis is a statement regarding a characteristic of one or more populations. We're going to discuss population proportions, population means, the difference between proportions, the difference between means, similar topics as to what we discussed with our bootstrap confidence intervals. With hypothesis testing, this is a procedure based on sample evidence and probability used to test statements regarding a characteristic of one or more populations. We're using sample data, so we're not able to determine what is the exact population proportion, what is the exact population mean. We're using, again, sample data. So we have two hypotheses here. The first one being the null hypothesis, denoted H naught or H sub 0. And this null hypothesis is a statement that we're going to be testing. The null hypothesis is always a statement of status quo or no change. Because of that, the null hypothesis is always going to be a statement of equality. So if you see the null hypothesis, this is including the equals. The alternative hypothesis, which some books denote H sub 1, other books denote H sub A, is the statement that we're trying to find evidence to support. Based on the context of the actual statement, this could be that it's greater than, that it's less than, or that it's simply not equal to the null. So, for our class, again, we have different ways that we can write these symbols. I'm going to call this the ho and the ha. H sub 0 and H sub A, the ho and the ha. Okay. We have three possibilities here. Equals versus not equals hypothesis, we'll call this a two-tailed test, and we'll see why in a few minutes. We start with some parameter, and again, the parameter is the value for the population. We're going to say that this is equal to some value. The null hypothesis is always a statement of equality. If based on the context here, I'm trying to support values that say that it's simply not equal to, then the alternative hypothesis is that the parameter is different from the null, simply not equal to. My second possibility, equals versus less than. This is a left-tailed test. The null hypothesis, again, statement of equality. The alternative hypothesis, H sub 1 or H sub A, is that the parameter is actually less than. Notice here, if this is left-tailed, the inequality points to the left. For my greater than, again, the null is a statement of equality, and my alternative is that it's greater than. If it's right-tailed, the inequality points to the right. So based on the direction of the inequality, I know whether the test is going to be left-tailed, whether the test is going to be right-tailed, and if it's not equal to, it's going to be two-tailed, and we'll see why in a few moments. The null hypothesis is, again, a statement of status quo or no difference. This always contains the equality. We assume that the null hypothesis is true unless we can show enough evidence to support that it's not. We seek evidence to support the statement in the alternative hypothesis. And again, why can't we simply determine what's the exact value? Because we're working with a sample data set. We're not working with the entire population. Okay. So what I want to do for these couple of examples is to read through the question and then based on the context, determine what's the null hypothesis and what's the alternative. Once we know the null and the alternative, you're going to tell me whether it will be a left-tailed, a right-tailed, or a two-tailed test. Okay, so let's begin. In 2008, 62% of American adults regularly volunteered their time for charity work. Researchers believe that this percentage is different today. Now, my null hypothesis is always a statement of equality. So if we go back, the null hypothesis is a statement of status quo, no difference. So the null hypothesis here is going to be that the population proportion is that 62%, or p equals 0.62. The alternative hypothesis is based on the context here. Did I claim that charity work has increased? No. Did I claim that charity work has decreased? No. I merely said that it's different. If you see the word different, you know that this is not equal to. So since the researcher merely believes that the percentage is different today, we have an alternative hypothesis of p is not equal to 0.62. It's different than 62%. If I have an inequality that's not equal to, it's a two-tailed hypothesis. Let's go through the second example. According to a study published in March 2006, the mean length of a phone call on a cellular telephone was 3.25 minutes. A researcher believes that that mean length has increased since then. If anything, for me, it's probably gone down. But let's take a look. The null hypothesis is a statement of equality. Now what variable are we looking at? We're looking at the mean. The population mean, we remember, is our variable mu. So the null hypothesis should be a statement of equality. It's that mu is equal to 3.25 minutes. Now, what does the researcher believe now? The researcher believes that this value is actually higher since 2006. So the alternative hypothesis would be what? That the mean has increased, that the mean is greater than 3.25 minutes. If that's the case, this would be a what? Right-tailed test. The inequality is pointing to the right. Take a minute and read through this. I'll give you a few seconds and then we'll go through the answer. Okay, let's see how you did. Using an old manufacturing process, the standard deviation, which is a way that we can measure the spread of the data, remember, of the amount of wine put in a bottle was 23/100ths of an ounce. With new equipment, the quality control manager believes that this standard deviation will decrease. The spread of the data will be smaller. When you buy a 750 milliliter bottle of wine, you're not necessarily getting exactly 750 milliliters. Okay, so the population mean, let's see if we can remember our variables. The population mean is our variable sigma. So what are we saying here? For the null hypothesis, a statement of equality would be that sigma is equal to 0.23 ounces. With new equipment, the quality control manager believes that this is decreasing. So what would I say about sigma? That sigma is going to be less than 0.23 ounces. And again, look at the direction of the inequality. This would be left-tailed. Inequality is pointing to the left. Okay. So let's read through. State the null and alternative hypotheses, multiple choice. A customer service center claims that the mean time a customer is on hold is less than 2 minutes. The null hypothesis should always be a statement of equality. So right away, options B and D make absolutely no sense. The null hypothesis should be a statement of equality. The alternative, we believe that it's what, less than 2 minutes? Option A. Let's try another. Let's determine if this is left-tailed, right-tailed, or two-tailed. Determine whether the hypothesis test, given that the null hypothesis is that the population proportion is equal to 43 hundredths, and that the alternative is that it's greater than 43 hundredths. Well, what did we say? If I give you an inequality, if the inequality is pointing to the right, if it's greater than, then this is right-tailed. When I do this hypothesis testing procedure, I'm not necessarily always selecting the correct result. And that's because I'm dealing with sample data. I'm dealing with incomplete data. If I had the entire population's data set and was able to work with that, I wouldn't have to do a testing procedure. I would know what the mean is. I would know what the population proportion is. But because I'm working with incomplete data, I'm not always going to make the correct decision. There's 4 possible outcomes from hypothesis testing. Let's go through what all 4 are. 2 of them we made the correct decision, and 2 of them we did not. Option 1. We rejected the null hypothesis when the alternative hypothesis was true. So the alternative was true, and we correctly rejected the null hypothesis. This is the correct decision. Option 2. We failed to reject the null hypothesis when the null hypothesis is in fact true. Notice the wording here. We failed to reject. We didn't accept the null hypothesis. We failed to reject the null hypothesis. We didn't have enough evidence to say that the null wasn't true when in fact the null was true. So we made, again, the correct decision. Our next 2 options are our incorrect choices. We rejected the null hypothesis when the null hypothesis was actually true. So we said there was enough evidence to reject the null hypothesis when the null hypothesis was actually the true statement. We call this a type 1 error. This is obviously an incorrect decision. This is a type 1 error. And for option 4, we failed to reject the null hypothesis when the alternative was true. We didn't have enough evidence to support the alternative hypothesis, so we failed to reject the null hypothesis, but the alternative was actually the true statement. This is what we call a type 2 error. We have a nice little box on the next slide that'll help us organize these statements. So let's look box by box. The null hypothesis was true, but we rejected it. This was our type 1 error. We're later going to see that this maximum type 1 error is what we're going to call our variable alpha. The null hypothesis was true and we failed to reject it. We made the correct decision. The null hypothesis was false and we rejected the null hypothesis. We made the right choice, we correctly rejected. And the null hypothesis is false and we failed to reject. This would be what we call our type 2 error. The maximum type 2 error is a variable beta. We won't work directly with beta, but if you like to look at outside resources, if you see that beta value, that's our maximum type 2 error. Okay. So let's say never accept the null hypothesis. This is tricky wording here, but we want to be very careful about what we're stating. We never accept the null because without having access to the entire population, we actually don't know the exact value of the parameter stated in the null hypothesis. Rather, we say that we will fail to reject the null hypothesis. Just like if we're in a court of law, nobody ever declares a defendant innocent. They either say that they're guilty or that they're not guilty. We either have enough evidence to say they're guilty or we don't have enough evidence to say they're guilty. So we're never saying that the null is true. We either have evidence to support it or we don't. Picking the correct language. Let's look at our example. Our example says, according to a study published in March 2006, the mean length of our phone call was 3¼ minutes. The researcher believes that this value has increased. We already showed in a previous slide how to make the null and the alternative. Let's see how I would summarize the answer based on these two possibilities. With option A, it says, suppose the sample evidence indicates that the null hypothesis should be rejected. So based on the procedure, and we're going to get into the nuts and bolts of how we're going to determine whether or not to reject coming up, let's write our conclusionary statement. So suppose that the sample evidence indicates that the hypothesis should be rejected. If we're rejecting the null hypothesis, we're saying we have evidence to support the alternative. The statement in the alternative hypothesis that the mean call is greater than 3¼ minutes. Since the null hypothesis is rejected, and here's the key part here, there is sufficient evidence to support the claim that the mean phone call is greater than 3¼ minutes. That's your headline. That's your major result of this statement. There is enough evidence to support the claim that the mean phone call length is greater than 3¼ minutes. Let's try our second example. Suppose the sample evidence indicates that the null hypothesis should not be rejected. Am I saying that the null is true, that it's exactly 3¼ minutes? No. What I am saying is that I don't have enough evidence to state that it's higher than 3¼ minutes. So, what would we say? In other words, the sample evidence is consistent with the phone call being approximately 3¼ minutes. There is insufficient evidence to conclude that the mean value is greater than 3¼ minutes. The key word here that I want to make sure that we put in, we fail to reject the null hypothesis. We don't accept the null hypothesis, we fail to reject. How are we going to determine where to reject and what to reject? There's two different procedures that can be done. One of which is the classical approach. The classical approach, in my opinion, is more visual, but it relies on us using tables of data that we haven't used all semester. Instead, we're going to go with the p-value approach. And the p-value is the probability of observing a sample statistic as extreme or more extreme than the one under the assumption of the null hypothesis. So I'm going to give you some type of sample data And then based on the null hypothesis, the p-value will be the probability of getting that sample statistic or a more extreme sample statistic. We're going to be using StatKey to find the p-value. This is not something we will compute by hand. In a traditional Stat 1 course, this would be something you would find on your own. P-value method. If I have a right-tailed test, the p-value is simply the proportion of the statistic in the distribution that is greater than or equal to that sample result, that sample statistic. Another easy way to state that, it's the area to the right. The area to the right is the sample statistic. So what would the left-tailed test be? The p-value is the proportion of the distribution that is less than or equal to the original sample statistic, or the area to the left. So what is my two-tailed test? My two-tailed test is that the p-value is double the proportion of the smallest tail. So these tails will be the same, or approximately the same size. So when we find this two-tailed test, we'll simply double the smallest tail. Let's take a look. Left-tailed test, p-value is going to be what? The area to the left of that sample statistic. Right-tailed test, the p-value is going to be the area to the right. Two-tailed test, I have rejection regions on both sides. Because it's not simply greater than, it's not simply less than, I'm saying it's different. So we simply double the area of the smallest tail. I typically just double the area of the tail on the left. It means the same thing. Statistically significant. A test is considered to be statistically significant when the p-value is less than or equal to the level of significance known as alpha. We said alpha previously. Alpha is that maximum type 1 error. So if the p-value is less than alpha, we're actually going to reject the null hypothesis. What are we saying here? What we're saying, again, that p-value is what? The probability of observing a value that extreme or more extreme. If that probability is less than that maximum type 1 error, then we reject the null hypothesis. Otherwise, we'll fail to reject the null hypothesis. Now, we can make that maximum type 1 error whatever we feel is appropriate, but the standard maximum error that's used in many research fields is that 0.05 or 5%. 5% of the time we'll make the type 1 error. And what is that type 1 error again? Rejecting the null hypothesis when the null hypothesis was true. If I set the alpha value to 0.05, what I'm saying is that 5% of the time I'm expecting to do this. So we're going to find the p-value using StatKey. And when we find this p-value, if the p-value is smaller than our maximum type 1 error, we will reject the null hypothesis. Otherwise, again, we don't accept, we failed to reject the null hypothesis. So randomization using for population proportions using StatKey. So we were in StatKey last lecture, and we saw bootstrap confidence intervals. We'll see if we move one column to the right, we'll see randomization testing. So we'll do randomization testing for a single proportion first. We'll go through examples of each. We're going to insert our data and insert the null hypothesis. And then we're going to generate our samples based on the original sample data that was given. The same way that we generated samples with our bootstrap confidence intervals. Again, I'm going to recommend using that Monte Carlo, the 10,000 bootstrap samples. The more samples that we generate, the more accurate we'll be. So we'll generate samples, and then based on the context of the question, we'll pick the proper tail, left tail, right tail, or two tail. The p-value is the probability of observing a sample statistic that extreme or more extreme as the one is under the assumption that the null hypothesis is true. So what we have to do is just edit the cutoff to match our sample data at the end. So let's go through an example. In 1997, 46% of Americans said they did not trust the media when it comes to reporting the news fully, accurately, and fairly. I would say that I would expect this number to be much higher in 2020. In a 2007 poll of 1,010 Americans, 525 did not trust the media. At an alpha value of 0.05, is there enough evidence to support the claim that the distrust in the media has increased? Now, if the alpha value here is not given, for this course we're going to assume it's 0.05. But I'm going to try to make sure that I supply that each time. But if you don't see it, assume it's that 5%. Okay, so let's go into StatKey. We are in StatKey. What are we doing? We're doing randomization hypothesis tests for this wasn't a mean value, this was a proportion. 46% of Americans, single proportion. I want to edit the null hypothesis. Let's state what is the null hypothesis here? Null hypothesis is a statement of equality, so the null hypothesis should be that the population proportion is 46% or p equals 0.46. The alternative, I'm claiming that this has increased. So this alternative should be what? Greater than 46%. If I have something that's greater than, I know that this will be a right-tailed test. So let's go back. Insert my data. What did we say? 525 out of 1,010. Again, that was in the edit data. My null hypothesis is always going to be set at 0.5. We have to change that to match our question. Our question was what? 46%? The null was 0.46. I can't select the tail until after I generate my samples. So let's generate samples. Our randomization sample, and again, I'm going to do that Monte Carlo 10,000 samples. If we go back, this is a what? Greater than? So this is a right-tailed test. This cutoff is not the cutoff that we're using. What was our cutoff? Well, our cutoff is based on our original sample data. And our sample data has a value of what? 0.52? 52% from the sample distrusted the media? If this is my cutoff, the box above is going to be the area to the right. This is right-tailed test, the area to the right. So what is the area to the right here? Well, it's approximately 0. What are we saying? We're saying that if the null hypothesis is true, what's the probability that this sample would have actually given me 52%? It's nearly 0. It's a highly unlikely statement. So let's go back into our slideshow. You can see that we have the same value. So now that we have this value, And when we do our randomization samples, not everybody's samples will be the same, right? In this example, I only had 5,000 samples, and what we just did, I had 10. But I can still see that the p-value was still approximately 0. Well, what does p tell me? If p is less than alpha, we reject. Otherwise, we fail to reject. What is my alpha value? My level of significance was 0.05. P is less than alpha, which means that we have enough evidence to reject the null hypothesis. There is enough evidence to support the claim that Americans' distrust in the media has increased. So I would first say we reject the null hypothesis. There is enough evidence to support the claim that the distrust in the media has increased. And again, what are we doing? We're just simply comparing p to alpha. What's the probability that I would have had a sample data that large given that the population data was actually 46%? It's nearly a probability of 0, highly unlikely. Example 2. A statistician claims that at least 77% oppose replacing a $1 bill with a $1 coin. Now, I was interested in this question last semester when we had this in class. I'd be curious to see how many people actually support this. Now, to see if the claim is valid, we randomly selected 80 people, and 55 of those 80 opposed replacing the coin. At a level of significance of 0.05, test the claim. Now, this is where these questions get tricky. We have to determine the null and the alternative hypothesis. The null hypothesis is a statement of equality. What am I told here? I'm told what? A statistician claims at least. What is an at least statement? That's a greater than or equal to 77% or higher. So that 77% has the equality in it, which means that the alternative has to be the statement without the inequality, or without the equality. The alternative is strictly an inequality. I could have written the null hypothesis as greater than or equal to 0.77 or strictly equal to. It doesn't change how we answer the question, so I always write the value as strictly equal to. But the alternative, because this was what, 77% or higher for the null, the alternative is less. So this is going to be a left-tailed test. Let's go back into StatKey, and I'll start from the beginning. In StatKey, we're doing a randomization test. Again, this was a single proportion. This was proportion data. We said that 55 out of 80 opposed. And our null hypothesis, again, was 77% or 0.77. Let's generate our samples. I really wish StatKey had a 10,000 button, but we just have to select this 10 times. If you have 9,000, if you have 11,000, you're going to get very similar values. When you find the p-values, if they don't match identically to my questions on the homework and on the exam, that's fine. Remember, we're doing a randomization sample. So your sample data may not be exactly the same as my sample data when I generate 10,000 of the samples. But the values should be very similar to each other. Okay. Going back to our question, this inequality was left-tailed, right? Less than. This is a left-tailed test. And now we need to make sure that the cutoff point matches our sample value. Our sample value was 0.688, and that's always going to be in the top right corner if you don't want to compute it by hand. If I do this, what's the p-value? What's the area to the left? 0.061. That p-value is greater then my level of confidence. That's more than 6%. You could see that the p-value when I did this question previously, very similar. We're off by what? 5 thousandths? It's still clear whether I'm going to reject or fail to reject. The p-values don't necessarily have to be identical because our samples aren't the same. Because p was greater than alpha, what would we say? There is not enough evidence to reject the null hypothesis. We cannot support the claim that the value is less than 77%. We can't say that it's not at least 77%. Again, we're not saying that it is. When I failed to reject, we're saying that we can't prove that it's not. Let's deal now with a second variable. Rather than dealing with the proportion, let's deal with a mean. The only difference when I'm dealing with mean data is that I actually have to insert all of the sample data. It's not a proportion where I can simply insert the sample size and the number with that characteristic. I have to copy and paste in all of my data. So let's take a look at our example. The mean wait time at a drive-through fast food restaurant is approximately 83.3 seconds. A manager devises a new drive-through system that he believes will decrease the wait time. We take a sample of 10 randomly selected orders and record their wait time. And these are our 10 orders. So let me quickly copy these orders. So we have the data copied. Let's see. Let's first write our null and alternative hypothesis. The null is always a statement of equality. We're dealing with the mean wait time, so my variable should be mu. The mean wait time, the null hypothesis should be a statement of equality. Mu is equal to 83.3 seconds. Why did the manager devise this new method? To decrease the time. So this would be a left-tailed alternative hypothesis. I have my sample data here. Again, let me quickly make sure that I have this value copied. And I'm going to just directly insert this into StatKey. Start at the beginning. Randomization test. Now I'm dealing with a mean value. Test for a single mean. I need to insert my data. I'm going to just delete anything that's already here and insert my data. I don't have a header row right now, so I'm going to make sure I deselect that. We said that we had 10 data points. Let's make sure we have 10. We do. What was our null hypothesis? 83.3 seconds. We change our null hypothesis, and then we generate samples. Remember, we can't select the tail until after we have our samples. This question was less than, so this is left-tailed. We have to change our cutoff to match our original sample data. Our original sample data had a mean of 78. So let's change our cutoff to 78. That was the average wait time. What is the p-value here? Well, for a left-tailed test, the p-value is the area to the left. What am I saying here? I'm saying over 12% of the values, if the null hypothesis is true, would be less than or equal to 78%. That's not going to be enough evidence to support the claim that it's actually different. And you can see I have slightly different values, off by, again, 5 thousandths. It's not going to change whether we reject or not. Because p is greater than alpha, and again, my alpha value, my maximum type 1 error we said was 0.05. And if we said if the question didn't state it explicitly, to assume 0.05. So because my p-value is greater than my level of significance, there's not enough evidence to reject the null hypothesis. Based on the sample data that we have, we can't support the claim that the fast food drive time wait has actually decreased. We don't have to do 3 and 4 examples for the same technique. We understand now if it's a mean value, we simply have to insert the data. I'd like to go through an example of the difference between two means. If I have the difference between two means, my null hypothesis is always going to be that the two means are actually the same value, that mean 1 is equal to mean 2. The alternative is going to be that they're not equal to each other. So let's take a look. We're going to use a built-in data set that's already in StatKey, so we don't have to insert data. We'll use an example that they already have in the website. Is there a difference between males and females in terms of the number of hours that they work per week? Sorry, number of hours that they exercise per week. Let's test this claim at a level of significance of 0.05. So I use subscripts here of M and F for male and female. The null hypothesis, again, is a statement of equality. It's that the two means are equal to each other, that men and women exercise the exact same amount of hours per week. If I'm asking you, is there a difference? I'm asking you, are they different from each other? Are they not equal? So let's take a look at this question. I'm going to pull up StatKey. Test for difference in means. Now, I said I wanted to use the built-in data set, so I'm not going to enter my own data. Instead, remember we have our drop-down menu. We're going to use a data set that's already in StatKey. Hours exercised, males versus females. X1 minus X2 is equal to 3. Males versus females, so what are we saying? Based on the sample data, men worked out an average of 3 hours more per week than women. Let's enter our samples. We'll do 10,000 again. Let's look at our hypothesis. Is this left-tailed, right-tailed, or two-tailed? This was our first one that was strictly not equal to, right? Just a different value, which means that this will be two-tailed. Now I have to enter my cutoff here. What did I say? From my original sample, the difference in the means was positive 3. So I'm going to change my cutoff here to positive 3. Change the positive cutoff to positive 3. And what do I see? I see that each tail here is 1/10. Remember what we said, if we have a two-tailed test, I double the length of the smallest tail. The tails are the same size. So the true p-value here is actually going to be what? 2/10? And again, you can see that I have slightly different p-values here, but it's the same general question, right? The p-values are going to still be similar enough that it's not going to change whether I reject or not. So we double the value of the tails. When I did the sample this time, I had, what, exactly 0.2. Here we have 212 thousandths, a difference of 12 thousandths. It shouldn't change whether we reject or not. And again, we're doubling because this is two-tailed. P was greater than alpha. My level of significance, again, was 5%. What are we saying here if we go back? I'm saying the probability that if the null hypothesis is true, that my sample values would have fallen in the tails, was over 21%. So that's not an unlikely result. So because this result is so actually likely to happen, we would fail to reject the null hypothesis. There's not enough evidence to support the claim that the mean values are different. If we had a larger sample size, maybe we would be able to show a difference, but based on the sample data that we have here, we're not. So this lecture, if we go to our syllabus, was the lecture for both hypothesis testing and for randomization testing. The homework for this section, or these combined sections, will be posted this week on WebAssign, along with a quiz on our bootstrap confidence intervals. If you have any questions, reach out to me on WebAssign, reach out to me on email. Let me know if you have questions. I'm more than willing to work with you through these email questions or arranging a, say, Zoom video conference where we can talk back and forth. All right. Stay home and stay safe, everybody. Good luck.